All right, welcome everyone to the final page for the fall semester 2014 final exam here in Math 234. In this problem, we're going to try to find the surface area of a nice paraboloid that lies above the plane z equals -13. So remember, anytime you want to calculate out a surface area, there's two ways to do it, right? If you have a surface that's parametrized, right? This is where you use the magnitude of the cross product of the partial derivatives of your parameterization, right? And that's very messy and it takes some time. Or if you have a nice explicit equation for your surface, let me do that in blue. But if you have a nice explicit, right, z equals, or if you can easily solve z equals, right, then there's a nicer way to do this. And so that nicer way to do this, right, so again, surface area is going to be the integral over some surface of 1 ds. And so remember, ds, this is the thing that we can interpret in two different ways. So this is going to be 1, and with our explicit equation, this is going to be the square root of g sub x squared plus g sub y squared plus 1 dA. And then this will be over the two-dimensional region in the xy plane. So this right here is our g equation, the thing that z is equal to. This is g. So let's go ahead and start evaluating this out a little bit. So 1 and the square root of g sub x squared. So okay, if I was to take the partial derivative of this with respect to x, I think I would get just -4x. Forgot my negative sign. -4x, and I need to square that. G sub y squared, so this is going to be -4y, and I need to square that, plus 1. One more line of simplification here. And let's see, well, 1 times anything is just that. And so I'm going to have 16x squared plus 16y squared plus 1 dA. And now we can see that I need to evaluate out this double integral, just x's and y's in it. So I need to decide on how am I going to do this. Well, that's where we actually need to maybe draw a picture of this thing. So let's go ahead. So let's see, lies above the plane z equals -13. And I'm wondering, okay, well, what would it take for it to lie above the plane z equals -13? So z equals -13 is, of course, maybe like way down here. And I could go ahead and maybe draw, something like this, a nice plane down here. So there's the plane z equals -13. And we have this paraboloid. And maybe if I was to sketch this paraboloid here, let's see, 5 minus 2x squared minus 2y squared. So this is going to be the paraboloid. It's shifted up 5. So 1, 2, 3, 4, 5. And then it's flipped over, right? Because this is negative 2x squared and negative 2y squared. So this is going to go down something like this. Pretty steep, right? Because it's -2x squared and -2y squared. So we're going to have something like this. So our paraboloid is going to be something like this. All right, so let's go ahead and see then where these things intersect. What kind of information can I get out of this? So if z is equal to -13, so -13, if that's equal to the paraboloid, right? I'm kind of interested in this curve of intersection here. So I'm going to have 5 minus 2x squared minus 2y squared. And so let's go ahead and maybe rearrange things a little bit. So I'm going to get 2x squared plus 2y squared is equal to, and if I go ahead and add 13 to both sides, I'm going to get 18. Let's go ahead and divide by 2, and we can see that this is going to be a circle of radius 3, right? Because it's equal to 9, aka 3 squared. So if I was to take this paraboloid, right, again, I'm trying to figure out what is the surface area of this paraboloid here that lies above the plane z equals -13. If I was to take this, and remember, I'm doing a double integral here over dA, right? I only have x's and y's. So if I was to smash this into the xy plane, right, I think that this would come up like so. Something like this. Let's see, I'm missing one of them. Here we go. And if we were to smash this, we would smash it into the xy plane here. And this is where the residue would live, right? So, I mean, we would have kind of residue, or kind of the paraboloid would be inside of this region in the xy plane after we did our smashing. Okay, so notice that kind of the outermost radius, I suppose, here for the circle is 3, right? Because that's going to come, that's where this paraboloid is the widest. All right, so at r equals 3, that's where kind of, again, this is the widest. This is going to be how maybe we exit this region. So now I can really sketch this in maybe the xy plane here. And so we get something like this. Again, after we smash, oops, that's not the highlighter. There we go. We're going to get something like this. So this is the region that we're integrating over. And now especially, right, we probably already had this as a hunch because we saw the x squared and y squared and everything. But now we really see that we're going to do this with a polar integration, right, a polar integral here. So let's go ahead and switch this out. And I'm going to do the square root of 16r squared plus 1. That's all under our square root. And then dA, I'm going to trade in for r, dr, d theta. We're going to integrate our r values from 0 to 3. And then our theta values, well, this goes all the way around the circle, so this is going to be from 0 to 2 pi. Again, we can see there's really no thetas anywhere in here, so if you integrate 1 with respect to theta, you get theta. You plug in 0 and 2 pi, we're just going to get 2 pi, so that's very nice. Now our r integral is going to take a little bit more time. Technically, this is a u substitution, but we're going to do a little bit of guessing and checking here to see what we get. So I'm going to go ahead, and I know that this is going to be 16r squared plus 1 raised to the 3/2 power, because it used to be here raised to the 1/2 power. And so if I was to take the derivative of this, let's see, I would need maybe a 2/3 to cancel out when that 3/2 comes down. And then when you take the derivative of the inside, you're going to have a 32r. Well, I like the r, that's supposed to be there, but now 32, I need something to cancel with that, so I'm going to do 1 over 32, because again, we don't see a 32 up here. All right, so I think this should be our correct antiderivative. Of course, you can take the derivative one more time just to double check, right? Be a little bit paranoid. And then we're going to evaluate this from 0 to 3. So, okay, let's see. There's a bit of cancellation here. I have a 2 and a 2, but then I have 32 in the denominator, so that's going to cancel out to be 8 in the denominator. So 8 times 3 is going to be 24 in the denominator, and in our numerator, just pi is left over. When I plug in 3, let's see, I'm going to have 9 times 16, which should be 144, plus 1, so I'm going to have 145. That's going to be raised to the 3/2 power. And then I'm going to subtract away when I plug in 0. Well, when I plug in 0, I'm going to have 0 plus 1. So it's just going to be 1. Raise that to the 3/2 power. This is going to be minus 1. And so here is my final result. This is going to be the surface area of the part of the paraboloid that lies above the plane z equals negative 13. All right. One last question to go. Here's a given vector field. Let S be the sphere. Use the divergence theorem to evaluate out the flux. Right? So actually, again, this is probably telling us too much, right? Let's imagine really quick if it didn't say any of this, right? It didn't specify use the divergence theorem, right? But it just says evaluate this the surface integral of our vector field over the surface. We have to remember that because the surface here, right, is the entire sphere, it is a nice closed surface, right? It bounds some three-dimensional region, aka it doesn't have, right, so this surface right here doesn't have any boundary itself, right? It bounds the 3D region, which is the sphere and its interior. We can use the divergence theorem on this. So we can go ahead and trade in this surface integral for the triple integral of div of f dv. So, and this is going to be over the three-dimensional region. So let's go ahead and calculate out the div of f. So I'm going to go ahead and take the partial derivative of the first component with respect to x, the partial derivative of the second component with respect to y, and the partial derivative of the third component with respect to z. Y squared plus z squared plus x squared. This is nice, right? So this is, of course, we could rearrange this and we get x squared plus y squared plus z squared. We're integrating over the sphere, right? And its interior here. This is a three-dimensional region. So I'm going to choose, of course, spherical integration. So this right here is the same thing as rho squared. And I'm going to have times rho squared sine phi d rho d phi d theta. And let's go ahead and look at what our bounds would be. So rho is going to be from 0 to 2. Phi is going to be from 0 to pi, and theta is going to be from 0 to 2 pi, because this is all the way around the sphere here, so this is kind of the most classic setup for spherical integration. So yes, this is very, very nice. Let's go ahead and do the integrals here. So again, we notice that there are no thetas anywhere. We're just going to evaluate out the theta integral really quick and get 2 pi. If I integrate out the phi integral, right, so the integral of sine phi is going to be negative cosine phi. And we're going to evaluate that from 0 to pi. And then if I was to evaluate out the row integral, right, so we're going to have rho to the 4th here, so I'm going to have 1/5 rho to the 5th power, and we're going to evaluate that from 0 to 2. So there's me doing the triple integral in just one step. Very nice, right? So let's see, I'm going to have 2 pi. When I plug in pi in for cosine, I get out -1. So minus a -1, that's going to be +1. And then I'm going to subtract away a negative, so aka plus, cosine of 0. So cosine of 0 is 1. Times, let's see, if I plugged in 0, I'd get out 0, so that's very nice. When I plug in 2, well, 2 to the 5th power is 32. So I'm going to have 32 over 5. Again, technically minus 0 here. You don't have to write that down if you don't like. So let's see, I'm going to have 2 times 2 pi, so that's going to be 4 pi, times 32 over 5. So 4 pi times 32 over 5. And we can simplify this down a little bit more if you'd like. Right, so let's see, 32 times 4 should be 128 pi's over 5. So there we go, that is my final answer. This is the flux, or the surface integral over this vector field on the surface. And of course we use the divergence theorem in order to calculate this out. All right, that's it for this video, and that's it for the final exam. I hope you guys enjoyed. Good luck. See you next time. Hopefully.